In the previous video, we talked about the basics of the wave equation, which is this complicated looking partial differential equation. And this is the wave equation in one dimension, which means that it propagates either in the plus x or the minus x direction, depending on the sign of the velocity. And it propagates in time, which is why you have the time variable here. And we also saw the solutions of the wave equation can be functions of either x plus vt or x minus vt. Now, a special kind of solution is called the sinusoidal solution to the wave equation, and let's talk about that in this part of the video. And that would be written as y of xt equals some constant known as the amplitude. Sine or cosine, I really don't care what I want to use there. I'll just put cosine for fun. K times x minus omega t plus some phase factor called phi. So that would be an example of a sinusoidal solution. And mind you, by taking the phase to be appropriate, I can make this cosine into sine. So the word sinusoidal does not necessarily mean you need to have a sine instead of a cosine. You can just have either a sine or a cosine. All trigonometric versions of sine and cosine are called sinusoidal. Let's just be clear on that. Now, this is a solution of that wave equation. So let's try to make sure that it is. Well, it's not exactly x minus vt. It doesn't look like x minus vt. It looks, by the way, I could have put plus also here, plus or minus. I'm just choosing one, the forward moving version, okay? And let's recall why this is forward moving. As time increases, omega t is going to be more and more negative, and so to keep your eyes fixed on the top of the wave, you need to go to the right, and going to the right means positive velocity to the right. Let's quickly verify why that it satisfies the wave equation. So if I take del y by del t, I'm differentiating with respect to time. So I'll get, first of all, cosine becomes negative sine, so negative a. And then when I differentiate with respect to time, I'll get a negative omega outside times sine of the same kx minus omega t plus phi. Let me differentiate it once more. Del 2y over del t squared. The two minus signs cancel out, so that's a omega squared. A times omega. And now when I differentiate again, I'm going to pull a negative omega out here. So I get that times cosine of kx minus omega t plus phi. Let me rewrite that. That's going to be negative a omega squared cosine kx minus omega t plus phi. So I'm done with the time derivatives. Let's move on to the space derivatives. First del y by del x. I'll again get a negative sign because when you differentiate cosine, you'll get negative of a sine function. So negative a, and then when I go in and differentiate with respect to x using the chain rule, I'm going to get the k outside. So ak times sine of kx minus omega t plus phi. And now I'll take a second derivative, d2y over del x squared. And this time there'll be another factor of k that comes out. So that's negative ak squared cosine, because the derivative of sine is a cosine. And that's kx minus omega t plus phi. And now to satisfy the wave equation, I should feed this to this side and that to that side. Let me do that. And let's see what happens. Therefore, I get negative a omega squared cosine. I'll just not write the arguments to save space. And that's equal to v squared times, because there's a v squared here, all this stuff. And that's negative a times k squared times the cosine of those arguments. So you notice the cosine simply vanishes. The a also cancels out, as does this negative sign. So I'm left with the very nice expression for what the speed of propagation is. It's plus or minus, I'll just take the plus sign, omega over k. That's a concrete formula for the speed of propagation. Now, omega is the same omega that occurred in simple harmonic oscillation. So if you put k x this equal to 0, A cosine omega t plus phi. That's exactly simple harmonic oscillation. So omega actually is 2 pi over the period t, or it can be written as 2 pi times the frequency of linear oscillations. K, which I'll be talking about soon, is something else, and K is given as 2 pi over a quantity called lambda, and there's also a version involving something else, and that's called 2 pi times the wave number, nu. So I'll just not get into the wave number very much. I'll just talk about 2 pi over lambda. Now let's try to understand these two. How do you get that, these two relations from something like that? So it pays off to examine the sinusoidal wave under two conditions. And I can think of these two conditions so that I reduce the complexity of this. So first, let me photograph the wave. If you photograph the wave, then you get rid of the time variable. Basically, you're saying I take a snapshot of it at some time t equals t naught. So the wave simply becomes y as a function of x. It's no longer a function of time, and it's going to be a cosine kx minus omega t naught, where t naught is fixed, plus phi, which I'll call it's a new phase, phi prime. So I can combine the negative omega t naught and phi into a new quantity called phi naught. So that's buried within phi naught is the old phase. So this can be easily conceptualized in a drawing. If I draw y as a function of x, then I'm going to get something like this. So in this photograph, so you fly in a helicopter and take a photograph of the ocean, you're going to be, if you're a surfer dude, you want to know how big the waves are, well, that you'll be able to see. The amplitude A will show up either as the crest or the depression or the trough, as it's called. So these are got names. This is called the crest of the wave, and that's called the trough of the wave. You can see these things by just looking at the snapshot. Okay. The other thing you'll be able to see is because this is the x coordinate, you'll also be able to see what's called the wavelength of the wave, how big these waves are separated from each other. So if you are surfing here, when is the next big one going to come your way? So that's another thing that you can figure out. So the wavelength is defined as the distance between either a crest and a crest or a trough and a trough. And my favorite way of finding the wavelength is to find out where it intersects the x-axis. So that's a pretty sure shot way of finding the wavelength. So that's called the wavelength lambda. It's literally the length of the wave. The next way of looking at this wave, so I've been able to get so far the wavelength and the amplitude by looking at the photograph of the wave. The second way of looking at the wave is somehow get rid of the x and keep the time. So here I think of it as looking at the wave between two tall buildings. So imagine you're going to a built-up ocean resort and there's very little space. Nobody can see the ocean unless they actually book one of the hotel rooms. And between two tall buildings, you can just barely see anything like the ocean. And that you'll just see the water level going up and down with respect to time. So that's the simple harmonic aspect that you'll be able to see very clearly in this. So here we are fixing x equals x naught, the location of the chink between two tall buildings. So let's draw a picture of that. The time coordinate, and this is y now as a function of t, where y as a function of t would be a cosine. Remember, now we are freezing space, so kx naught plus phi will become something, and I'll try to keep the negative sign with that. So this will be cosine of omega t plus some new phase phi double prime, where phi double prime would be negative phi. I have to be careful here, negative kx naught. Okay, I've transfer the burden of the negative to that. The cosine of a negative theta is the same as cosine of theta, so it doesn't bother cosine any, which is one of the reasons I chose cosine instead of sine. I didn't want to deal with messy negative signs. So once you have this, you can simply plot this graph, and it does not have to start like that. It can start somewhere else. So this is going to be looking like that. Now in this graph, what can you see? Remember, the x-coordinate is now time. So you'll be able to see the period. The period is the time taken to go between two successive crests. That's probably the best thing to use in this case because of my drawing. So that you can see that there. You can also see the amplitude in this thing, because if you see the wave between two tall buildings, you are going to be able to find out how big the wave is by just looking how high it goes up and how deep it goes down from the mean position. So you're going to be able to figure out if you have a big one or not in terms of waves, even if you're just looking at the wave between two tall buildings. So in this case, you'll be able to see t, and omega is 2 pi by t, and it's equal to 2 pi f, and here the relationship here is that k equals 2 pi over lambda. So whatever you're able to see occurs in the denominator of whatever you have in the wave equation. You have k in the wave equation, but what you're able to see is lambda in the frozen profile, and so k is equal to 2 pi over lambda. Here you have omega in the wave equation in the profile where x is fixed, and so t is what you readily see in the picture, and omega is 2 pi over t. So those are things to remember or just observe. Now let's write everything. Let's write this. This is sometimes called the wave relation. It's a very famous thing, as opposed to the wave equation. So please don't call this the wave equation. That's the wave equation. That's the wave relation. Now let's write the wave relation using our newfound variables. So I'm going to write the wave relation as follows. It's currently it's equal to omega, v equals omega over k. Now omega is 2 pi f, and k is 2 pi over lambda. So what I'm going to do is I'm going to write it in terms of the new variables, because that's simply the more common way of doing it. So this is going to be 2 pi f divided by 2 pi divided by lambda. So the 2 pi's will cancel out and the lambda will come upstairs. So f times lambda. And there I've written one of the most celebrated equations in all of physics. The speed of propagation of a wave is equal to the frequency of the wave times the wavelength of the wave. Now let's try to use this in a simple example, very simple example. I want to find how big. So let's say I'm shopping for a music system. All right. And the salesman says, oh, buy this music system. It's really good. It can reproduce 20 hertz. The speakers are so big, you can get 20 hertz. Well, let's make sure we understand how big the wavelength of a 20 hertz wave is and see if we can truly hear it, because to hear a wavelength of 20 hertz, frequency of 20 hertz, you must have enough room for the wavelength of 20 hertz to actually fit in your house. So let's make sure before we get carried away and buy a speaker that costs lots of money. Let's find out how big the wavelength is going to be. So lambda, which is what we're trying to find, is the speed of sound, which I told you in the previous video is 343 meters per second in dry air and so on, divided by the frequency, which is 20 hertz. And right here you see the problem. 343 over 10 is 34.3, and 34.3 over 2 is something like 17 meters, and that's about, I don't know, something 50 plus feet. So your room should measure at least 50 feet in size, okay? And most people don't live in houses where the music room is 50 feet in every direction. Okay, that's a very big music room. It's almost like an auditorium. So truly speaking, you can only hear these 20 hertz waves in an orchestra hall or something like that, because that they do have that much space in a big auditorium or someplace like Eastman Kodak Auditorium you do have 50 plus feet between walls, and that can comfortably fit one entire wavelength of this 20 hertz wave. So yes, go ahead and buy that expensive speaker, but what you're really hearing is some muddied sound from the wave reflecting off the walls, and all that muddy sound you're going to hear as low frequency extension. It's not going to be a true 20 hertz by a long shot.